Welcome to Advanced Embedded Systems. Today is lecture 25, where we'll be talking about direct digital synthesis. So today, after you do your time logs, we are finishing up post-scope control, lab 3. Functionality is due by close of business today. And then the write-up is due on Friday. You can still turn in functionality late and just make sure you upload in your README documentation of completion. And make sure you're also pushing your files if you want me to run it. Also, Monday, lesson 27, our project proposals are due, so keep that in mind. If you look at the website, all that's listed on the syllabus, so you have project ideas link. You can also look at the lab 3 functionalities due today. Monday we have the write-up, and then a project proposal is due beginning a class on lesson 27. So, you take a look at the project page, click on that. Final project proposal page, and take a look. There's lots of documents on here to take a look at. It overviews what you're supposed to do for the project. Ultimately, you're going to design and implement a engineering prototype that addresses some need, using the things you know about displaying and interface with some other peripheral device and make it drive the display in a certain way to address some sort of need. When you look at the project ideas page, you click on that, there's lots of different project ideas from previous years, either videos or just plain descriptions. Take a look at those. Your proposal, your initial proposal, it's not the final one. So this is your project proposal, initial one. And then we're going to revise that based upon feedback. So, on both of those pages, you can look at the final project document, which has a template. The final project report will not be written in Markdown. It will be written in Word, and that's fine. But take a look at the guidelines. It shows what's on the website for each of those documents that you're going to be writing throughout this, which is your proposal, then your plan, more detailed, your different milestones, and then the presentation in front of class, and then the write-up requirements. Proposal, it's just written in Word, and it looks just like this. What need are you fulfilling? Some marketing requirements, level 0 description, basically talking about the inputs and outputs to sensors and modules of your design. You'll also have a state diagram or a flow chart that describes the behavior of the system, probably both, just in your level 0 description, where you're going to have graphics that actually describe how things are interconnected. When you take a look at this, make sure you're looking at the final project rubric, which is also posted on there. The proposal, to get all the points, the 5 points for the proposal, show all attributes of the proposal, cover sheet, need statement, marketing requirements, and level 0 description and flow graph. So I want to see an actual diagram of how the system works, and that'll just be block diagram of, hey, taking this input to our board, Xilinx board, and outputting it to the display. Not that detailed. Okay, so back to the lesson today. We are going to talk about fixed point arithmetic and multiplication, as well as the direct digital synthesis and phase increments to create those waveforms. And basically what we're learning in the next few lessons is signal generation. So First, we'll talk about fixed point numbers, which you already know. You have numbers that are coded in binary. Like this example here, it's 5 bits, but it encodes as a decimal number. You can determine that value of that number in decimal by using an equation, right? So our decimal value is going to be the sum of each bit, so b sub I times 2 to the power of I. You're going to have the sum of all the bit positions in that number, starting from right to left. And that least significant bit here is always index 0. So you have 2 to the power of 0, which is 1, times whether it's a 1 or a 0, right? So if we convert this number, sum of products, sum of all the bit positions to get the value in decimals. So we have 1 times 2 to the 4th, 0 times 2 to the 3, 0 times 2 to the 2, 1 times 2 to the 1, 0 times 2 to the 0, and we get 16 plus 2, and eventually 18 out of that. But we can also generalize this idea for the right side of that decimal point. So what do you think 1.11 means? Basically, it means just like in decimal, the numbers to the right are a fractional portion of a bit. So, everything to the right of that binary point, well, in decimal, if it's up to the right of a decimal point, it's going to be using a negative indice, so a negative power, and it would thus show you a fractional portion of 10, right? You have the tenths, hundredths, thousandths position to the right of the decimal. Binary works very similarly. So in this case, we have 1, so this bit position 1 times 2 to the 0, and then 1 to the right of the decimal, we're going to just index by negative 1. 1 times 2 to the negative 1, which is 0.5, right? And then 1 times 2 to the negative 2 gives us 0.25, or a quarter. And we add all those together, and this binary fixed point value represents 1.75. So now we have fractions. But how do we convert, say, a number like 1.53125 into binary? We do it the same way you convert from decimal to binary, basically using our tried and true technique to find the lowest power of true, 2, that will fit into the number, and then subtracting that value, right? So we go through, we do this until we get down to 0, or as close to 0 as we can, or if we run out of bits. So to illustrate this one, the largest power of 2 that fits into this is going to be 2 to the power of 0, which is 1. So we subtract that off, and we're left with 0.53125. And the largest power that fits in that is 2 to the negative 1, which is 1/2. After that, we're given 0.3125, 0.03125, and the largest power 2 is 2 to the negative 5 that fits into that, and that's 0.03125. Thus, our binary number is 1.10001. Right? We don't have a 2 to the negative 2, 3, or 4. So those 3 bits are 0. This in DSP is called a Q1.2 format. If we have another number, say 5 bits of whole number and then 4 bits of fraction, that would be considered a Q5.4 format. And we can also take this value, this larger number, and find a decimal value. For this one, all we're doing is multiplying the bit positions, and I just reduced all the zeros just to make it a little cleaner to look at. So we have 1 times 2 to the power of 3, 1 times 2 to the power of 1, then 2 to the negative 2, and 2 to the negative 4. Notice we start here left of the binary point at 0, and we go negative to the right, and then positive to the left to increment those values. That gives us an 8, a 2, a 0.25, and a 0.0625. Add them all together, and we get 10.3125. All we have to do is keep track of where the binary point is on our fixed point decimal, or fixed point binary. What about if you have a negative number and we want to convert it to a Q8.8 format? What do we do then? Forget about the negative for now. We're just going to look at 13.3125. Find the largest power of 2 that fits in that. We get an 8. So that's 2 to the power of 3. And then we get a, subtract that off, we have 5.3125. And we get power of 2, so a 4 in there. Subtract that out, we get 1.3125. And now we pull out a 1, which is 2 to the power of 1, giving us 0.3125. And then we can pull out a 0.25 out of there, which is 2 to the power of negative 2, which gives us 0.25, giving us 0.0625, which just happens to be 2 to the power of negative 4. Subtract that off, and now we just plug in our numbers, and it represents 1101, so 13.0101. 2 to the negative 2 and 2 to the negative 4. So that is for a positive 13.3125. How do you make that a negative 2's complement number? A fixed point, it works the same as in regular binary numbering systems. You flip all the bits and add 1 to that least significant bit, which just happens to be the one to the very right, even though before we were adding 1 to the 1's position, exact most negative position. So if you flip these bits and add 1, you're going to get, take those, flip all the bits, and then you add 1. Notice these 4 bits would have been 1, but we added 1 to them, thus shifting that bit to the left 1 more bit. So this is the final value, and that's Q8.8, so we can represent that in a 4-bit hex value as well, F2B0, which is negative 3.125 fixed point. So, remember we have this number in binary Q8.8 format, 13.3125, it's represented as this. What if you have a binary number that was in Q16.0? What would you get? How would you get that number into a 16.0 format? All you have to do is shift those numbers to the left, or to binary point to the right by 8 bits. So if you shift that number from here to the right by 8 bits, you're essentially multiplying it by 2 to the 8. Right? So you can shift that number to the right, so you're multiplying 3.3125 times 2 to the 8. We're getting a 3408 when we shift it right by 8 bits. This value, I take the calculator, I'll even show you this. Show this in programmer mode. We have 3408. Convert that to binary. Notice we get the same number we had before. 1101, 0101, 0000. And that's our 16-bit number. So, this number, this binary number in fixed point to 8.8 format is the same number as 3408. You just don't have to deal with the fractional portion. If you multiply by the value that you're shifting that binary point, then you can convert it using whole numbers instead of fractional bits, right? So this is 8 bits of whole, 8 bits of fractional portion. Right, so this is whole. Represented the same way, we just have to make sure we track where that binary point is. So it works in reverse as well. So if I divide 3408 by 2 to the power of 8, or multiply, we're going to get that 13.13125. Otherwise, we can also multiply by 2 to the negative 8, which basically moves that binary point to the left, back to where it was. That binary point doesn't actually exist. It is only exists to the programmer who's defining it. Okay. So as you can imagine, some real rational real numbers do not have to have a binary representation. Right? The decimal number of 0.1 cannot be represented as a finite string of ones and zeros. It would essentially repeat endlessly. Just like when you're in the power of 10, you can sometimes, 1/3 is 0.33 repeated. So we can have sometimes that we're just going to either have to round it up or round it down to that last bit, depending on what system we're fitting in. So we're truncating our numbers essentially. So fixed point arithmetic. Fixed point numbers versus floating point. I'm not going to do a floating point in this class. But how can you represent a number? We can represent numbers with fractions even when the hardware resources are limited. So we don't need to use, say, a 64-bit floating point or a 32-bit floating point. We can use an 8-bit or 16-bit value and reduce the amount of hardware that we're going to need. Again, fixed point arithmetic, we're going to have whole bits, whole 7 down to whole 0, and then fractional bits, F7 to F0. Right? The W bits represent the whole portion, and F bits represent the fractional portion. This 16-bit number can be manipulated as a whole with minor bookkeeping to keep track of that binary point. Right? It doesn't really exist. We just have to know where it is for our calculations. This, given, is our Q 8.8 format. So, as an exercise, we're going to add a couple numbers. We're going to add 23.5 and 45.25 in the Q 8.8 format. Convert them, and then add them. So, 23.5, right? And I'm not showing the binary point, just have a little space there. But to add these up, convert that, you have the whole portions, 23, and then 0.5 on the fractional portion, for those 8 bits. And then we're going to line up that binary point, or that radix. So then we have 45 for the whole portion of 45.25, and then 0, 1 for the fractional portion, to the power of negative 10. 2 is 0.25. We're going to add these just like we added before. Add the least significant bit to the most significant bits, and just add them and carry over to the next higher bit. So as you're going through, you have 1 and 1, or 0 and 1 gets a 1, 1 and 0 gets a 1, 1 and 1 gets a 0, carry the 1, 1, 0, 1, 1, 0, gives us a 0, carry the 1, we get a 1, carry the 1, 1 and 0 gives us 0, carry the 1, 0, carry the 1, 0, carry the 1, and now we have this number, which translates to 68.75 in decimal. Okay. So that binary point, again, I didn't show it here because it doesn't really exist. Make sure when you're adding numbers that you line up those binary points. But line them up and add bits normally, just like in regular binary addition. How do we do multiplication with fixed point numbers? So we can assume assume that 23 you have a 4-bit representation where the binary point resides in the middle of the number. So we're going to use a Q2.2 format just to make it a little bit smaller and a little bit easier. We're going to multiply a couple of numbers together. When you do these, I would actually multiply them in decimal and then multiply them in binary just to make sure you get the right result. So the way we do it, so we convert our values, so it's Q2.2, so the 3.25. And apparently I have that one backwards, so it should be 3.75. 3.75 multiplicand, and then convert 1.25, so you got 1, and then 0, 1 for the 0.25 is the multiplier. Multiplier and the multiplicand. Remember back when you did decimal multiplication in grade school, you basically started the least significant bit or digit of the multiplier, and you're going to multiply that by everything on the top, the multiplicand, and then you're going to shift left to the next digit of the multiplier, multiply it through, shift again. It works the same in binary. So the first line, I'm going to have 1 times everything on top. 1 times 1 is 1, so we're basically going to copy it. So 1 times 1, 1, 1, 1, 1 gives us 1, 1, 1, 1 on the output. Then we're going to shift left by 1, so we can start looking at the 0 bit, that second bit digit. And then multiply 0 by anything, it becomes 0, so we just put 4 zeros in here. But we shifted left by 1, right? Shift and add. Next one, we have 1, shift left once more, 1 times 1, 1, 1, 1, 1 on the top gives us 4 1s. The next one, shift left, we get 0 times everything, gives us zeros, and then we just look at the columns and add the bits together. So we are going to get a 1, and a 1, 1 and 1 becomes 0, carry the 1, gives us a 1, carry the 1, gives us a 0, carry the 1, and to here, and then 0, carry the 1, gives us a 1, and then add a 0 to make the result fit in a Q4.4, because if we have 2 bits of whole and 2 bits of fraction for each of those digits that we're multiplying for numbers, our product would require double the fractional portion, double the whole portion to be able to fit that product into that result. Thus we get 46,875. So we have 3.75, and we're multiplying that by 1.25. We're going to get that same number if we use a calculator. Right? But what if the multiplier is the wrong size? Right? What if we only have a, say, a 16-bit or a 8-bit multiplier, or a 16-bit multiplier, but our operands are bigger. So let's consider this with a two 16-bit fixed point numbers. So half of that is the whole part of A and the fractional part of A and the whole part of B, fractional part of B. How do we multiply that out to get a result that is 32 bits? And actually break it up into parts, and we're going to multiply out the fractional part of A and B, and then shift that. We're going to have the whole part of A, fractional part of B, whole part of B times fractional part of A, or add that, shift it, and add that to the whole part of A and the fractional part of B. That's how you would do the wrong size, if you had the wrong size multiplier. Just break it up into components and multiplying it out. But if you have a hardware multiplier that fits the size, then you're just going to do a lot of shifting in that. Again, for this one, if you have 16-bit floating point number, the product would require 32-bit. So you're shifting left by 8 for these portions here. You're doing this multiplication. What if you don't have two operands that are the same fixed point? What would be the product of that? Let's say you have a Q0.8, which is no full portion. Multiplying by Q2.2. What would the product mean? So if we multiply them together, Q0.8 minus Q2.2. We're going to get a 2 for the whole portion. So how much range we're going to get 10 bits for the fraction. So we're just going to add the fraction portion together. Alright, next we are going to talk about direct negative synthesis. This is a technique used to create periodic waveforms with very precise frequency control using a system with a fixed clock frequency. We're going to store that function in a lookup table similar to this down here. This is basically an int8 sine waveform. So int8, so it's only going to go up to values of 28. We're going to use all unsigned values. So we're going to store it in the wave lookup table. This is an example of a sine wave. This is what that sine wave looks like. So we go from 128 to 256, down to 0, and back up to 0.28. And these are all the values. There are 64 values in this array that represent this sine wave. Table length has to be a factor of 2 to the n to make it work. So in this case, we have 2 to the 6, 2 to the power of 6, which is 64 samples in our array. We broke up our waveform into 64 parts to represent it. We're going to use something similar to this in Lab 4, where we're going to build our function generator. We're going to basically store our VRAM. We're going to store this sine wave, similar to what we showed on the previous screen, in our VRAM, in our hardware. And we're going to have that signal on ready, so we know our audio codec is at 48 kilohertz. It's a fixed frequency of the ready signals, right, when we're running in. We're going to have D out from our VRAM tied to that L bus in, And every 21 microseconds, which is the inverse of the frequency, we're going to have a bit going out, or basically 18 bits of bit representing our sine waveform being output. Our counter, what you had before, where you take the random read address, you only have 10 bits there. But in our C code, we have 16 bits for our address, so we can utilize. And these other 6 bits were used, were basically trashed. But we're going to learn in the next few days how to use those to increment, do partial incrementing through these arrays to be able to interpolate these signals and draw them out a little bit more. So we're going to use a radix point in those fractional 6 bits to do that. If I have 64 elements in DRAM, my period to print those 64 elements to the display would take roughly 1344 microseconds. So that's 21 times 64. Invert that, so that's microseconds per cycle through the whole waveform. Gives us a frequency roughly of 744 hertz output. Alternatively, if you had 1024 elements in DRAM, you could actually print at 21 milliseconds per cycle, roughly, which gives us 48 hertz. We're basically dividing 48 kilohertz by 1,000. Right? Roughly at 48 hertz. I actually took my Lab 3 oscope and I dropped in this waveform into the C code, and it was printing out as basically in the 744 hertz. And it prints out the waveform. It's a little bit more scrunched together, but it just basically printed out that waveform over and over again into the DRAM to generate a sine wave output. Doesn't do anything else other than that. Lab 4 is going to change. We're going to learn how to change those output waveforms, their frequency and amplitude. First thing we're going to learn about to do this is phase incrementing. So how did I increment through this waveform in my C code to be able to print that into DRAM and then put that onto the screen? So if you think about how that audio codec provides a 48 kilohertz signal through an interrupt, that ready signal comes in at 48 kilohertz, and then we can output more data to that audio codec at that frequency. But we need to increment through our sine table by 1 on every input. So how long would it take to get through the table? I learned about this on previous slides. It's going to take basically 1.3 milliseconds, right? Through the period. 1.344 microseconds per cycle. 64 elements. And if you 21 microseconds per update gives us that. So the increment through the entire table would take about 1.3 milliseconds. That generates our sine wave around 750 hertz. If you incremented the pointer through our sine table every 2 interrupts, so basically we're dividing that by 2, right? So we're waiting and updating it every other, or output every other ready signal. How long would it take to get through the table? It's going to take twice as long to get through the table. Sorry. If we're incrementing our pointer in the table by 2, every init, not every other init, but every init, we're just indexing by 2. So we're skipping a value and going to the next value in the table. So we only have 32 values multiplied by 21 microseconds to give us 65 milliseconds, so half the time, double the frequency. This frequency is about 1.5 hertz, so almost double that value, or 1.5 kilohertz, double the 750 hertz. And this works well when you use integer values to increment. This gives very coarse adjustments to our frequency. Let me show you in the lesson. So on the lecture notes, we have a spreadsheet here for direct digital synthesis. You can take a look at that. You open it up to the DDS page. I can show you giving a phase. So this phase is our increment value. So we're going to increment by 1 into this array. And you can see the lookup table for our array, right? Going from 120, basically 128, through to 255, down to 0, and back up to 128. Right? If I increment by 1, we're going to output 1 waveform, and this will be at 750 hertz, because there are 64 elements or samples in the lookup table. If I index that by 2, we're actually going to print 2 waveforms in the same period of time. So this frequency is doubled to 1.5 kilohertz. The problem is, I can index by, I can't do fine adjustments. So what if I put in 1.5? Then we start getting some issues because we're not indexing from 1 to the next or skipping a value. So 1 to this value to this value, if we skip by 2, right? Index by 2 would skip to these values in the array. 1.5 will get us somewhere in the middle. And you're going to get an output waveform that is a little bit rugged, right? So, what if you have wanted to generate a signal that was somewhere in the middle, about 1 kilohertz instead of 1.5 or 750? Right? We'd need to increment our pointer in the sign table every point 1.5 indexes every 21 microseconds. This can be easily accomplished with fixed point representation. We just add 1 bit to the right of the decimal binary point. But this value, this fractional value, is going to be our phase increment. Fractional phase increment. So let's look about how this looks. So let's look how that phase increment, our update rate, and the size of our lookup table are related to our output frequency. We're going to be given a lookup table with 2 to the power n values corresponding to 1 waveform of the function. We're going to have a sampling rate or a playback rate. That's our frequency of sampling, updates per second. In our case, we have 48 kilohertz. That's defined in our audio codec. And then we're going to have this phase increment that will happen every 1/f. Right? 1/f is a period, so this happens, this increment will happen every, in 48 kilohertz example, is every 21 microseconds, essentially. So we're going to add that to our index, to our lookup table, and then index to that next value. So, put it in our formula. We got frequency samples, that's updates per second. We have values per update, so we're going to index by so many values per update. And then we have our cycles per 2n values. This is defined in the firmware, right? It'll be the wavelength of our function. as defined by how many values we have in our lookup table. Frequency updates per second, that's going to be our playback rate. That's hard-coded or in the hardware, not audio codec. It's defined during update rate. The only value we can actually change is our phase increment. That is how much we're going to index into that lookup table per update. Right? This X essentially becomes our function generator knob, where it just dials in the frequency that we want. Right? So, we got some questions. So, assuming update rate 48 kilohertz, level of 1024 entries versus the 64, and a phase increment of X. And we're going to express it as a 10.6 fixed point number. We're going to answer 4 questions. We're going to try to get the maximum frequency we can generate, the minimum frequency, what's the smallest change in frequency, we can make with the phase increment, and how do we generate a specific frequency given those values, and then I'll talk about how we arrived at that formula for phase increment, that 10.6. So, given our sampling is 48 kilohertz, which is our audio codec, and we're going to have 2 to the n, 1024 values in our VRAM, which is a good value to have. You want to have as many samples as you possibly can. We're going to use 1024. First thing we're going to do is find X to generate a 440 hertz signal as a 10.6 fixed point number. So, what goes on? Generates that frequency. So you know F frequency over 2 to the n, so 48 kilohertz over 2 to the n, 1024 gives us 46.875. This is a number we're going to use quite often, and it's not really going to change. So 46.875, we multiply that by our X value. Okay, so we have 48 kilohertz. We're basically just molding this and this section together. And then we have values per update left over to give us our result in frequency. Our frequency is sample rate times X over 2 to the n hertz. Right, so on the right hand side of that we have 440 hertz, and then we combine that frequency sampling and our 2 to the n values to get 46.875. And we divide it out, we get an X value of 9.387. So, how do you represent 9.387 in 10.6? This is the value you're going to get. Whole portion's pretty easy, right? 0.1001 for 9, right? And our radix, our binary point. And then on the right hand side, we're going to get 11001. If I wanted to do this, I could actually take 9.387 if I didn't want to use it in fraction, and divide it out to figure out those binary digits. I can multiply 9.387 times 2 to the power of 6 to shift that. Radix point over, so we get 600.768. So we'll call that 601. Right? You can round up or round down, or truncate down. So 601 decimal. Notice in binary that is essentially 9011001, which is what we got. That last bit can be a 1 or a 0, depending on if you round up or round down. Round up or truncate. Right? So this is essentially our index value. It's a 440 hertz signal. What's the maximum frequency we can generate with a 10.6 number? Given that we have a 10.6 number, you would think the largest frequency would be index value of 250, 512, right? But we can't use that, and I'll show you why. The largest value would be 256. So that's going to be 1 with 6 zeros, 8 zeros after it. 256. And that will roughly give us, we can't do this, but I'll explain it in a bit because of Nyquist theorem. We're going to get a 46.875 times that x value to get 12 kilohertz. So basically multiplying that out will give us a 12 kilohertz signal. Our frequency sampling is at 48 kilohertz. The highest frequency you could technically get, according to Nyquist says what? We must sample a signal twice the highest frequency, so 2 times the highest frequency. So if technically the highest frequency would be 12, I need to sample it twice that highest frequency to get our output signal, because the highest frequency, observed frequency or output frequency we can do would be essentially 24 kilohertz, half of the sampling frequency, because we're trying to represent a sound wave, right? So if I sample here and here, I'm just going to get a straight line. I need to sample twice that to actually get a good value out of this. So hopefully we get value here and then the extremes for 4 values with our Nyquist theorem. So the official highest frequency would be x equals 256. And that would be at 12 kilohertz, which is 1/4 of our sampling frequency. So our observed frequency is going to be 24 kilohertz. So we have to sample it twice then. Okay. What is the minimum frequency we can generate? Assuming 10.6, the minimum frequency would just be the very smallest number change, which would be 0.000001. So x is 2 to the minus 6, and that's going to give me roughly 0.73 hertz. What is the smallest change in frequency? The smallest change is going to be the same. The smallest phase increment change would be that least significant bit at 2 to the minus 6, thus giving us a change in frequency of 0.73 hertz for signals. So, how did I get to this format of 10.6 for our phase increment? Our RAM needs 10 bits of address. The standard to index through 1024 values of our standard 16-bit register would have 6 bits left over for that fractional portion. So you notice you have a counter, just like we talked about our VRAM. There are now 1024 values of some sine wave put in there. You have those extra 6 bits that were previously trashed. Those can be a fractional portion to index into these values into our array. So next time we're going to actually talk about indexing and doing fractional portions into that index and demonstrating that. So notice when we do index, so if we went from 1, the add index 1.5 doesn't really exist. The index 1.5 is between 1 and 2, so it would be somewhere between 1 and 2, depending on if you're truncating down or rounding up. you would actually get a sine wave that's a little jagged edged, right? So if you round down, 1.5 would have been here, then the next value would be 3, right? So 1, 0, 1, and you get 3 plus 1.5 gets me 4.5, and then 6, notice you're just jumping around a little bit as you're indexing to 1.5 and you're indexing 3. Next time, we're going to talk about interpolation, so actually rounding, averaging those values based on that fractional portion, so we get the green array, right? Waveform versus the jagged B, so we're going to just smooth out that waveform, or we're not going to interpolate the difference between them. And if you notice, values where you went from 0 to somewhere between 39 and 51, it's actually averaging that value to 145 to those interpolated values. And 163 was that third value. 163, and then somewhere between 175 and 186, we got 180. And so on and so forth. So we're going to go through that next time. Definitely download this spreadsheet and play with it. And we will go more in depth on that in the next lesson. Have a good day. And don't forget to get your finish your lab 3. I'm going to go around and see how you're doing on those for your functionality, and then by Friday, next time, you need to have your